All right, welcome to Lesson 6-1, and in fact, welcome to Unit 6, which is the last unit of study for this course. Now, Unit 6 is all about applications of integrals and antiderivatives, and really, Unit 6 is really split into a couple of different parts. The first half is going to focus on these things called differential equations, and more specifically, solving differential equations. The second half is going to focus on more applications in terms of area and volume. So while we talk about differential equations in the beginning, it's important to note that what we're looking at here regarding differential equations is a very, very basic introduction to the topic. You should know that there are entire college courses that are entirely devoted to just this idea of differential equations. So there is clearly much, much more to them than what I'm going to introduce to you here within these first few lessons. So just for you to keep in mind. Now, what the heck is a differential equation? So a differential equation is just an equation that contains derivatives. So not really surprising there. And because a differential equation is an equation, it is something that we can solve. And that means that a solution of a differential equation, just like a solution of any equation, is a function that satisfies the equation. Now, you're used to solving an equation and getting a value, like a number, x equals 5. For a differential equation, your solutions actually take on the form of a function. Now, it could be a constant function, so it could be something as simple as y equals 4, which kind of sounds a lot like a normal equation to you. But it could be also something like y equals sine of x, or y equals x squared. So the solution of a differential equation is actually a function, and it could be as simple as a constant function, or it could be something much more complex. Now, some examples of what a differential equation could look like. So we have a couple of examples right here. So this first one, dy dx equals 3x minus 5y. Now remember, dy dx is a specific notation that we learned way back in Unit 2 for a derivative. So this is an equation, because it has an equal sign, and it contains a derivative. In this case, it has dy dx, the first derivative of y with respect to x. So this would be an example of a differential equation. This is another example of a differential equation. Notice in this case it includes y double prime, it includes a y prime, and again it's an equation because it has an equal sign. So that's all that a differential equation is. So they can take on many different forms, they can look like a whole bunch of different things, but it will always include some sort of a derivative, whether it's using prime notation, whether it's using this dy dx kind of a notation. Okay, so now what does it mean to be a solution? Well, I have the definition there, but let's actually take a look at what it actually looks like. All right, so example 1, determine whether the given function is a solution of the differential equation. So this is really just a yes or no kind of a situation, or is it a solution or not? So our differential equation here is this is now the fourth derivative, just to make sure you're clear on that notation. You haven't really seen that a whole lot before because we haven't really gone beyond the second derivative. But remember, the fact that that exponent, it's not really an exponent, but because it's in parentheses, that's indicating that it's a fourth derivative. This is not y to the fourth. Okay, so please make sure that you notice the difference there. So this is saying the fourth derivative of y minus the second derivative of y equals 2y. So that's our differential equation, and our proposed solution is y equals sine of x. Now, to determine whether y equals sine of x is a solution of this differential equation, we're basically substituting in, very much like if you had this situation here. If you had the equation 2x plus 7 equals 11, and I ask you to check if x equals 3 is the solution, you would just substitute 3 for the x. And you would check to see, does the left side become the same as the right side? And you would clearly see that that does not happen. So in this case, x equals 3 clearly is not the solution of that equation. So we're doing the same idea here. So we're starting really by looking for the fourth derivative of the sine of x minus the second derivative of the sine of x. And we're checking, does that equal 2 times y, which remember is the sine of x. So to find the fourth derivative of sine of x, we actually need to find each of the derivatives. So off on the side, let's do that. So we know that y prime is going to be cosine of x. We know that the second derivative then will be negative sine of x, which we're also going to need reference to. The third derivative becomes negative cosine of x. And remember, we could also notate the third derivative with the 3 in parentheses. And then finally, the fourth derivative becomes positive sine of x. So the fourth derivative of sine of x is still sine of x minus the second derivative of sine of x, remember, was right here. That's going to be negative sine of x. And we're checking, does this equal 2 times the sine of x? Well, sine of x minus a negative sine of x does become 2 sine of x. So the two sides are equal, so yes, y equals sine of x is a solution of that differential equation. So let's go ahead and take a look at a second example here. So this time we've got the second derivative of y plus the first derivative of y equals 2y. And our proposed possible solution is y equals e to the 2x. So again, we're just determining, is y equals e to the 2x a solution of this differential equation? Well, in order to do that, we are going to need to find the second derivative as well as the first derivative of y. So let's go ahead and do that. So y prime will equal, so remember this is e to the u, so the derivative of e to the u is e to the u times the derivative of u, which I'm going to rewrite as 2e to the 2x. And that means the second derivative is going to be the derivative of the first derivative. So that's going to be 2e to the u times the derivative of u, which becomes 4e to the 2x. All right, so now when I substitute in, so the second derivative of y is 4e to the 2x plus the first derivative of y, which is 2e to the 2x, and we're checking, does that equal 2 times y, which remember is e to the 2x. Well, 4e to the 2x plus 2e to the 2x is 6e to the 2x, and that is not equal to 2e to the 2x. So in this particular instance, no, y equals e to the 2x is not a solution. All right, so that's what it looks like to have a differential equation and to check if a proposed function is a solution or not. But like I said, what we're going to focus on for the first few lessons of this unit is solving differential equations, or at least solving these basic differential equations. So today we're going to look at sort of a visual / graphing approach to solving differential equations, and it's using these things called slope fields. Okay, so our first example here, we're going to draw a slope field for the given differential equation at the indicated points. So our first differential equation we're going to draw a slope field for is dy dx equals x plus 1. Now, what a slope field is it's literally a field of slopes. It's going to be this grid, which basically looks like your coordinate plane. But at each of the indicated dots, you're going to see a little line segment that has the slope indicated by this differential equation. Because remember, the very first interpretation of the derivative that we had is that it's the slope of the tangent line. So what we're going to end up doing to start with, and at first this is going to seem very tedious, but after you see what I do, I'm then going to talk about how you can try to make some shortcuts. So basically what we're going to do is we're going to make a table, but that table is going to contain 3 columns. The first column is for x, the second column is for y, and the last column is for dy dx, the slope, which in this case is x plus 1. Okay, so now for x and y, we're just going to start choosing any of these points from this grid, and we do have to eventually do all of them. So I'm just going to start with 0, 0. So when x is 0 and y is 0, dy dx will be 0 plus 1, which is 1. And what that means then is, at the point 0, 0, I need to draw a segment, a line segment, that has a slope of 1. So remember, a slope of 1 means it would rise 1 and go over 1. So right here, I'm going to draw a little segment that has a slope of 1. All right, so that's the first one. And now we're going to just keep on going. So what about when x is 0 and y is 1? Well, notice in this case, it's still going to be 0 plus 1, so we're still going to just get a 1. So that means at the point 0, 1, I still have a slope segment with a slope of 1. So in other words, these two segments should be parallel because they have the same slope. Notice now, if x is 0 and y is 2, it's still going to be 1. So hopefully what you're noticing is that because this particular example, dy dx, is not in terms of y, it's only in terms of x, that the y doesn't actually affect the value of dy dx. dy dx is only affected by the value of x. And what that means then is that all of the points that have the same x value will have the same slope. So I don't have to now make additional entries for the other y values when x is 0. I know that they're all going to have a slope of 1. So I'm going to put a slope of 1 there and a slope of 1 there. So again, all 5 of these segments should have about the same slope, or they should have the exact same slope, but because we're drawing it manually, of course it's going to be slightly imperfect, but just do the best you can to make sure that these all look the same. Okay, so now, what happens if x gets bumped up to 1 and y is, let's just arbitrarily pick 0. So now, if x is 1 and y is 0, then dy dx is going to be 1 plus 1, which is 2. Now remember, a slope of 2 is a little bit steeper, right? That's going to go up 2 and over 1 to the right. So at the point 1, 0, remember this is 1, 0, we're going to have a slope of 2. So again, it would have to be as if I went up 2 over 1. So that slope is going to look something like that. Notice that it's a little bit steeper than my slope of 1, and that's how it should be. Okay, so no one is going to take a ruler and double check that your slope is exactly 2. What they are going to look for, though, is your slope of 2 steeper than your slope of 1? Because it should be. Now, remember, I don't have to figure out for 1, 1 and 1, 2, or 1, negative 1, or 1, negative 2, because for this particular differential equation, remember that y does not affect the dy dx value. So I know that this point right here also has a slope of 2. This point right here also has a slope of 2. Same thing down here, and same thing down here. All right, moving on. So what about when x is 2 and y is 0? Well, dy dx will now be 3. So again, 3 is very steep compared to 2. So 2, 3. So it's something like that. Again, it doesn't have to be perfect, but you do want to make sure that it looks slightly steeper than a slope of 2. So slightly steeper, still slightly steeper, and slightly steeper. All right, and then finally, on that side, when x is 3 and y is 0, then now we're going to get a slope of 4, which again is even steeper than a slope of 3. The one thing you don't want to let happen is don't let it go vertical. Okay, if you go vertical, you're now saying that it actually has an undefined slope, and that is not what it says. Okay. Now, let's go the other direction. So what about if x is negative 1? Well, negative 1 plus 1 is 0. Now remember, a 0 slope is horizontal. So that means everywhere that x is negative 1, we actually have a horizontal segment. And again, because y does not affect the outcome of dy dx, we know that all of the points that have an x-coordinate of x equals negative 1 are going to be the same. All right, and then when x is negative 2, we now get a slope of negative 1. So now we're going this direction. Okay, and again, no one is going to be measuring, but a positive slope should be going the correct direction. A negative slope should be going the correct direction. A zero slope should be horizontal. And a slope with a bigger value should be steeper than a slope that has a slightly lesser value. And then finally, just to finish this off, when x is negative 3 and y is 0, we get a slope of negative 2. So again, it's just going to be a little bit steeper, a little bit steeper, a little bit steeper. Keep on going and keep on going. Perfect. All right, so this is what's called a slope field. And this is a visual indicator or a visual guide to this differential equation. Now remember, I said that we are using this slope field to solve a differential equation. We're supposed to find what function would we be able to find the derivative of that would make this equation true. And the idea is a slope field should be sort of implying or indicating a particular function shape to you. If you look at this slope field, I certainly hope that it looks kind of like a parabola to you. And if you think about a parabola, what's the equation of a parabola? Well, it's something with an x squared in it. And if you take the derivative of something with an x squared, you're going to get something with just an x. So this slope field is a visual representation of the shape of the function that would be the solution. So in other words, a solution for this equation would have to be some sort of a quadratic function, something with an x squared in it. And that's what slope fields do for us. Again, they are a visual representation of the solution of that differential equation. All right, let's look at another one. All right, so this time we're going to look at dy dx equals x plus y. Now, unfortunately, unlike the previous example where dy dx was only in terms of x and we were able to find ourselves a shortcut, this time around dy dx is in terms of both x and y. And what that means then is that both x and y does have an effect on the slope. Okay, so again, in example A, when dy dx was only in terms of x, it meant that the y value had no effect on the slope. So whatever you got for one of the values of x, you knew that it was the same vertically. Similarly, if this dy dx were only in terms of y, if this was only in terms of y, then dy dx would only be affected by the y, and all of your slopes would be the same horizontally, as long as the y-coordinate was the same. Okay, but again, that is not the situation here. Now, it doesn't mean, though, that there aren't still going to be some shortcuts. We will still be able to try to look for some patterns if possible. And so it's just that the pattern might not always be a vertical or a horizontal pattern. It might be circular, or it might be on a diagonal, something like that. Okay, so how do we start off with something like that? Well, you can just start substituting all the different values, but I like to try to look for zero slopes first. So in other words, can I think of a combination of an x and a y that would make this 0? So for example, we know 0, 0 would work. So that means I know that at 0, 0, I will have a horizontal segment because that's a slope of 0. Now, can I think of another one? Well, what if x is 1? If x is 1, then what would y have to be so that dy dx is 0? Well, y would have to be negative 1. And now that would be a slope of 0. So that means at the point 1, negative 1, 1, negative 1, we would also have a slope of 0. So it seems like maybe we're going to have a pattern on the diagonal. So let's explore that. What if I used 2, negative 2? So if I use 2, negative 2, that would also be a slope of 0. So now that I'm starting to see that pattern, let's go ahead and just fill in the rest without having to make that in the table. So negative 1, positive 1, that's going to be a slope of 0. Negative 2, positive 2, that's also going to be a slope of 0. All right. So now that means we can now see that this pattern on the diagonal happened. So maybe, again, not guaranteed, but maybe we will see other patterns along that diagonal, and that might be something to consider as we go forward. So now let's try another one. So let's try 1, 0. So if x is 1 and y is 0, then that means our slope would be 1. So at 1, 0, I have a slope of 1. So if that pattern holds true, let's see what happens at, say, 0, 1. So at 0, 1, we're going to have 0 plus 1, which is 1. So that also gives us a slope of 1. What about at 2, negative 1? So if x is 2 and y is negative 1, then that's 2 plus negative 1, which is also 1. So that pattern again held. So it appears that this time around, the slopes along this diagonal have the same slope. All right, so that means I'm going to go ahead and fill in this slope right here and this slope right here. Again, you want to try to make them all as parallel as possible. So now, when at 2, 0, that's going to be a slope of 2. So again, that's going to be a little bit steeper than the slope of 1 that we just used. And assuming that the pattern continues, we're just going to do a slope of 2 along this diagonal. And right there. All right, and then at 3, 0, that's going to be a slope of 3. So again, even steeper. And we're going to make that along that diagonal as well. And then at 3, 1, that's going to be a slope of 4. So that's even steeper. Now, we do start to risk getting vertical. And like I said, just do the best you can, but we do somehow have to make it steeper than 3, which gets really difficult. And then here at 3, 2, that's a slope of 5. That's even more close to vertical. So again, just do the best you can there. Try not to let it go vertical. All right, what about going the other way? Negative 1, 0. Well, that's a slope of negative 1. So now we have negative 1, negative 1, negative 1. Notice these should actually be pointing at each other because this is a slope of negative 1. All right, what about at negative 2, 0? That's going to be a slope of negative 2. So make sure that it's a little bit steeper than your negative 1. There's a negative 2. There's a negative 2. And there's a negative 2. Oops, that is not a negative 2. There we go. And then at negative 3, 0, that's going to be a negative 3. So again, has to be a little bit steeper, a little bit steeper, a little bit steeper. Negative 4 and negative 5. All right, so again, this is our slope field for this differential equation. And the shape of the graph implied by this particular slope field would be your solution. Now, this is not necessarily a function that you would already know or recognize, but oftentimes they will be. All right, so this is how you form or generate a slope field from a differential equation. It's all about just substituting in the x and the y coordinates of each point into your derivative to find out what slope you get, what value of the derivative you get. And then you draw the little segment that has the slope indicated by your dy dx. All right, so another thing that you're going to be asked to do in your assignment for this lesson is you're going to be given a slope field that's already been generated. And the question is going to ask you to identify the possible solution indicated by the slope field or that the slope field represents. So for example, here we've got a slope field where all of the segments are horizontal. And so if you think about what kind of a function is implied by a horizontal line, well, that would have to be a constant function. So a possible solution might be something like y equals 3. Okay, now notice it says possible. So this is literally just asking what are all the possibilities. You're not going to have a question on your assignment or your test that's this open-ended. I'm just doing this for the sake of this example. So it could also be something like y equals 0, or maybe y equals -2. Okay, so all of these are implied by this slope field because all of these are functions that are horizontal lines. And this particular slope field is indicating solutions that are horizontal lines. Let's do another. So for this example, we have this slope field where it seems like the graph, if you kind of follow these segments, the graph kind of does this. Now, what function does that make you think of? Hopefully it's making you think of trig functions between sine and cosine. Now, specifically, remember that sine would start at 0, 0 and go up and then go down. And that's not what's happening here. Cosine, however, starts at 1 and it goes down first and then it comes back up. And that is what seems to be happening in this particular slope field. So a possible solution indicated by this slope field might be y equals the cosine of x. Okay, so when you are trying to match a slope field with the solution that it could represent, what you're really trying to come up with is that family of functions indicated by the shape of that slope field. So if you think back to pre-calculus and Math 3 and even Math 1 and Math 2, all the different types of functions that you learned when you learned all those different base graphs, that's where this is going to really pay off. You're going to be looking at these slope fields, and hopefully the slope fields are indicating to you one of the shapes of these base graphs that you've learned before. Okay, and finally, the last type of thing you're going to be asked to do is, if you already have a given slope field, you're going to be asked to draw a solution curve in the slope field that passes through a given point. So in this case, we have this slope field that you see in front, and we're talking about the point -1, 1. So the first thing you're going to want to do is plot that point. So -1, 1. Is right here. Now, that point in this particular example happens to land on one of the segments. That won't always happen. Sometimes it may be off of a segment, and that's fine. It doesn't really matter. But now, to draw the solution curve, the idea is, remember that your curve has to have each of these slopes as it passes through. So we need to use the direction of all of these segments to kind of point us which way the curve should be going. So what you're going to do is start with your pencil on the point, and first we're going to go sort of to the right or down, whichever way we're being pointed. Now notice this segment is pointing me downward this way, so I'm going to start by going this way. But now notice, as soon as I get to this diagonal there, you'll notice that now the slope is pointing slightly flatter at a -1 slope. So my curve needs to start going a little bit flatter that way. Oops, let me see if I can fix that. And then now notice, as I get through this diagonal, I now have a horizontal tangent. And remember, a horizontal tangent is going to happen where the graph sort of levels out or flattens out somehow. So by the time I get through this diagonal, my graph needs to flatten out. And then now, as I approach this, that almost looks like a slant asymptote, doesn't it? And in fact, that's exactly how we're supposed to treat it as we draw this solution curve. So as I approach that diagonal line, I'm going to flatten out right along it. I could have done a better job, but again, this isn't meant to be perfect. It's just meant to sort of follow along. So this is what the right side of the curve should look like. Now, I'm going to go back to that original starting point, and now I'm going to go the other direction. Same thing. First, this segment is pushing me this way, but as I get up to here, as I get up to this section, notice that it's pushing me slightly steeper. And then when I get above that, again, slightly steeper. So that means I'm going to go slightly steeper and then slightly steeper. So this right here would be my example of a solution curve in this slope field that passes through the point -1, 1. I cannot emphasize enough. You must make sure that you start at the point that your curve is supposed to pass through. Do not overlook that, okay? All right, let's do one more. All right, so finally we have this one. So we're going to try to draw a solution curve that goes through the point 0, -2 in this particular slope field. So again, first thing I want you to do is to start by plotting your point at 0, -2. So that would be right here. Now, when you look at this slope field, I certainly hope that the first thing you see is a circle. But what I cannot emphasize enough then is solutions to a differential equation must be functions. So again, that means we're not going to draw an entire circle, which is not a function. Okay, so what we are going to do is we're going to start going from our point that our solution curve goes through, and let's start by going to the right. Now remember, I'm starting at a horizontal segment, so that means I have to start flat. But as I'm going to the right, notice that these slopes are getting gradually steeper until I get to this x-axis, which seems to almost be vertical. Now, they didn't actually draw the vertical segments here, but you would probably see vertical segments there. Now, going to the left, same idea. So we're going to start flat. Oops. We're going to start flat, and eventually it's going to get a little bit steeper. Oops, got crooked. I'm going to get a little steeper, and then a little steeper, and then something like that. Okay, this was not very symmetrical. I did not do a very nice job drawing this, but I hope that you can still get the idea. All right, so there we go. So this would be our solution curve that goes through the point 0, -2. Now notice I did not keep on drawing. I did not go all the way around to draw a full circle. And again, that's because our solutions must be functions. So the fact that this was 0, -2 actually means we wanted the bottom half of a circle. If this were at 0, +2, we would have had the top half of a circle. Okay, so that is drawing a particular solution curve in a slope field through a given point. So on your assignment tonight, you'll notice it's in two different parts. One part is on a Google form, and that's where you're going to match differential equations with the slope field that it would generate. You're also going to be matching a slope field with the solution that it seems to represent. And then finally, part 2 of your assignment is in WebAssign, and that's where you're going to be checking to see if a proposed equation is a solution of a differential equation and recognizing which particular solution curve is correctly drawn. All right, good luck.